Chapter 4, we're going to continue with 4.2 area. So 4.2 is going to feel a little disconnected from 4.1. It's all going to connect when we get to 4.3. So just kind of, if you're feeling like this doesn't look anything like what we just did, you're right, it doesn't. So we're going to be looking at area today, and we're going to be looking at some notation that you may or may not be familiar with. This is sigma notation. So if we have the sum of n terms, a1 to an, we can write it with this sigma. I equal 1 at the bottom tells you where you start. The n at the top tells you where you end. And the a sub I is the notation in between. Whoops, I wanted that one. So this is our sigma notation, and this is what it means on the right-hand side. I is called the index, and then the upper and the lower bounds are the 1 on the bottom and the n on the top. So if the n value is small, it's usually easy enough to just count these up or calculate these up by hand. You're just finding the first 5 numbers added together, okay? Or something like that. If the number is large, that becomes a little bit more cumbersome. If you have an equation and somebody says, evaluate it at 1 and 2 and 3 all the way up to 100, and then add all those numbers together, that's not a very, simple thing to do, right? So depending on whether you've got a small data set or a large data set depends on how you kind of approach the problem. Not because both won't work, because both may not be practical. So the first thing we're going to do is one with something small, so you can see how it works when we work with small values. So we're going to find the sum from 1 to 6 of 3i minus 2. And we're going to do this by actually figuring out what is a1, a2, all the way up to a6. And we do that by putting the numbers 1 through 6 in for I. So the first one we have 3 times 1 minus 2. What does that give me? 1. The next one is 3 times 2 minus 2. 4. About 3 times 3 minus 2. 7. We'll do one more and then we're going to pause. 3 times 4 minus 2. 10. Do you see a pattern in the numbers I'm getting? They're increasing by 3. And that should make sense because it's 3 times the number I keep putting in, right? I'm getting 3 more every time. So if at some point you recognize a pattern, and on some of them you might, and on some of them you might not, but if you do recognize a pattern, you can just use that pattern to find the remaining pieces you need. So 13 and 16. And then what we're going to do is we're going to add those together. So have 1 plus 4 plus 7 plus 10 plus 13 plus 16. So whether you're doing it in your head, on paper, or with a calculator, what are you going to get? It is 51. Good job. Okay, so we could do this. We wouldn't want to do this all the way up to 100, right? So there's got to be another option for the up to 100 part of it that we don't have to actually, to do them all out. And there are some formulas for how we can actually do this in a quicker way when the values are very large. Right, a large number of n values. So the first one talks about what happens when we add together a constant. So think about what happens when you add 5 plus 5 plus 5 plus 5 a whole bunch of times. There's a simpler way to do that. What's it called? Not powers. You're close. Multiplication. Yeah. So if I add together a number a whole bunch of times, that's otherwise known as multiplication. So instead of actually adding that, I could just take that number c, whatever it is, and multiply it by however many of them I have, and that's n. And that one, you've got it written on your paper. I won't write it on my screen, but it's called the sum of constants. That's what that is. The next one is credited to a mathematician named Gauss. And it talks about what happens when we add the numbers together sort of increasingly. So we add 1 plus 2 plus 3 plus 4 plus 5 all the way up to whatever ending value that we have. Okay? So Gauss was 6 years old, and this is the way the story goes anyway. I think it's true, but it's the story. And he was in a first grade class, and the teacher wanted to give them an activity it would take them a long time to do. And she said, I want you to add up the numbers from 1 to 100, and that should take a first grader a long time to do. Agreed? And Gauss did not take a long time to do it because he was gifted with a mathematical mind, and he figured out how to do it in a different way. And this is what he did, or at least a variation of what he did. You take the number of numbers you have, okay, however many there are, you multiply it by n plus 1, and you divide by 2. He didn't do his multiplication. He did it a little different process, but this is the formula that results from it. So if he had 100 in his case, right, he would have taken 100 times 101 and divide by 2. Very clever way of doing it, and there's a patterning he did, is what it's done, but we're not going to do that. But he did this sort of patterning as a 6-year-old. I'd say that's a gift from God, wouldn't you? Because I wasn't doing anything like that when I was 6. All right, the next one is the sums of squares. So the number 2 is the sum of integers, the first positive integers. The next one is the sums of squares. So we're adding together 1 squared plus 2 squared plus 3 squared plus 4 squared and so forth. Now, you can't just say, well, let's just take the thing we did before and square it. Powers don't work that way, right? So just consider a real quick one. If you had 2 squared plus 3 squared, you do not get 5 squared, do you? You can't do that. You can't just add the pieces underneath and then square it afterwards. That doesn't work. So we have to have a different form which to do this with, but it is similar. You have an n and you have an n plus 1. Those pieces are the same. But you also have 2n plus 1, and it's all divided by 6. And then the last one is cubes, so the sum of the first n cubed numbers. And this one is n squared times n plus 1 squared over 4. Which, interestingly enough, actually is this one squared, isn't it? Do you see that? If I squared everything on the I squared one, I would get what I'm getting down here for the I cubed one. Yeah. Okay, so what are we going to do with these? Well, we're going to use them for problems like this, where the n value is larger than is reasonable for us to do by hand. And it's pretty obvious when it is. It's usually pretty significantly larger, like 16. 16 is probably large enough you don't want to do it by hand. 10 might be sort of like the in-between ground. It doesn't really matter. Most of yours will be even larger than 16, so you'll know for sure this is where I'm doing this. And I think the directions might also indicate to use formulas or something like that, like they do here. Use summation rules. Now, before you go finding the summation, we actually have to do some notation that makes the summation work. I can't just jump in and use pieces. I need to separate what I have. So the first thing I'm going to do is I'm going to separate all these pieces out. So I have this 5, I have this I, and I have this 4, and they all need to be separated so that they start to look like these specific pieces. So what does it look like? Well, the first thing is that we pull the 5 out into the front of the summation. My n equal 1 to 16, right? 16 is still here, and I have an I here. And then there's a subtraction sign, and then I separate the summation for the second piece of the summation, which is I equal 1 to n, to 16, excuse me, of 4. So why do they need to look like this? Well, they need to look like this because this and this are what I'm able to use these formulas with. Right? If I have the 5 in there, I don't have a formula that actually allows me to use it that way. And you want to be careful or you might misuse the formula because you're not interpreting it quite correctly. So once they're in this form, we can use those formulas. This says 5. So this one says that I have I equal 1 to 16. So 16 is operating like that upper number that they've called n on this previous page, right? So the n on the previous page here is my 16. So I'm using this formula because it is I, but the n is going to be 16. So I'm going to have 16 times 17 divided by 2. Is that okay? All right, the next one is a constant. It's the first one that we did here. It says I take that constant, whatever it is, mine's 4, and I multiply it by n, being the upper value on the top of my summation or my sigma. So this 4 gets multiplied by 16. So in these cases, the 16 up here is the n from the previous slide. Okay, so at that point, you're going to grab your calculator. You're going to multiply 5 times 16 times 17 divided by 2. And you're going to multiply 4 times 16, and then you're going to find the difference between the two of them. Now, it's possible that these differences can be fractions, they could be decimals, they could be positives, they can be negatives. All those things can happen. It just depends on the formula that you're working with. What does this one end up giving you? What do you have, Lauren? 616. 616 is correct. Okay, are we good? Okay, so what about number 3 is different? There's a couple of things. Maybe 3 things I can see automatically. Tell me something you notice that looks different. We don't have an I. That's an easy fix. Okay, so if you have a problem like this where it starts out of the N at the bottom instead of I, you can just change it. So feel free to adjust that so that that doesn't sort of distract you. This can be I, this can be I, and this can be I. Okay, it's just a dummy variable. It doesn't matter what it is. So feel free to adjust that. That's the first thing. What else is different? What? The 4 at the bottom. This one says that it's starting at k equal 4, or it said n equal 4, excuse me. Now mine says I equal 4. But these formulas are starting at I equal to 1. And it does matter where it starts. So we're going to have to make amends for that. I'll show you how to do that in a minute. There's one other small thing that we should probably be aware of. You rewrite it as I squared? Yes, you got it. Good. It's written in sort of a factored form, right? We need to distribute it out for it to start looking like those other pieces. So let's start with that, and we'll do our i's, like changing it to i's at the same time. So this is I equal 4. Okay, it will be 4 to 140. And then we've got I squared minus I. Okay, so what do we do about the fact that it starts at 4? This is what we do. We change it to 1. Now, we don't get to do that for free. There's a cost. There's a penalty to be paid. The penalty to be paid looks like this. Let me write the other pieces in first. I have automatically now included an a sub 1 and an a sub 2 and an a sub 3 that should not be there, haven't I? When I changed 4 to 1, I included 3 terms that are not supposed to be there. So the price to pay for doing so is that I have to subtract them off. I need to subtract off A1 and A2 and A3. Okay, so it's like equations, right? You add something to the left, you have to add it to the right. So if I've included extra with the summation, I have to subtract the extra off. Okay, it's just like that. So I am going to need to figure out what A1 and A2 and A3 are, and this is as good a place as any to do so. So you can use any version that we have, either the factored version or our distributed version. What is A1 going to be? It is, it's 0. So we didn't have to pay very much for that one, right? If we had forgotten that one, it wouldn't have been a problem. But what about A2? Not 2. It's not 4 either. right, what did somebody say? Did somebody say 2? It was 2? Okay, it's 2. Sorry, I was looking at something wrong. I apologize. It is 2. You're right, it's 2. I was already onto the 3, I think. How about 3?
6.
That one's the 6. That's the one I was thinking of. Yeah, cool. Sorry, I don't mean to confuse you. I promise I don't. All right, so this piece in the middle here now, or not the middle, the beginning, we actually have to use those summation rules. And we have to separate it out just like we did on the previous problem. So we're going to do the summation from I equal 1 to 140 of I squared minus the summation from I equal 1 to 140 of I. And then I'm going to subtract off the 3 numbers that I just found, minus 0, minus 2, and minus 6. Okay, this first one, the I squared, we haven't used that one yet. At least we haven't used that property. It's the third one on here. It's n times n plus 1 times 2n plus 1. What's my n in this problem? 140. Okay? So in this one I have 140 times 141 times what? What is 2 times 140 plus 1? Somebody said it. What? 281? And all of that's over 6. And then the I one, we've used that one before. That's the one we used last time. That's the n times n plus 1 over 2. So again, it's very similar to the starting part of what we just did. It's the 140 and the 141. So 140 times 141 and divide by 2. And then we need to subtract off the 0, 2, and 6, which is an 8. It's 8 at the end. All right, so go ahead, use your calculator, because now you don't want to do that in your head, probably. 140 times 141 times 281 divided by 6, minus 140 times 141 divided by 2, minus 8. What will that give you? It's a large number. What do you have, Lauren? Let's see if you're right.
895,562.
Not quite. You're close, though. Yeah, just try it again. 612. Yeah, it's 900,000. So 612. So be careful with your computations. There's a lot of pieces that we're working with. Feel free to stop at different points if you wish, instead of doing it all in one massive piece in your calculator. Sometimes parentheses trip us up, those kind of things. So it will be 914,612. So what in the world does that have to do with calculus? Because, I mean, it's summations, and we haven't done anything with that. And so it actually has to do with finding area. The title of the section is called area. So again, I'm going to merge these two pieces together. So pause for a moment. We've looked at the summation notation. We're going to look at another piece, and then we're going to pull them together. We're going to look at the area of a plane region. So the idea is that we would want to take these two hash marks down here. I'll call them A and B. And we would like to draw these vertical lines here. And we would like to find the area between them under the curve. Okay, this is our goal. Our goal is to figure out how to find this area. And spoiler alert, this area is related to what we did last time with antiderivatives. And we'll connect them next time, or it may be in section 4.4, I can't remember. 4.3 or 4.4, we're going to connect them. But they are connected. So we're going to try and find these areas by doing a numerical approach first. Now, we did numerical approaches to slope back in section 1, like 1.1 of the entire semester. And you might remember using your calculator and it being sort of tedious. And then we had derivatives, and derivatives found it without the numerical approach. That's what's going on here too. We're going to try and find this area with a numerical approach, and then we're going to use antiderivatives, and we're going to actually be able to find it exactly without all the hassle. Okay, so this is the hassle section. So here's what we're going to do. We're going to create rectangles within this shape that are going to approximate what we have here. So we end up having, let me try that again. Here we go. I'm going to draw it with 4 because 4 is an easy one to imagine. We're going to split it into fourths like this. And then we're going to draw vertical lines that go up like this. And we're going to have this same picture drawn multiple times. So I'm going to go ahead and paste mine in these times so that they're the same on all my graphs. Okay, there's nothing special about 4. I could have drawn 6. I could have drawn 7. I could have drawn 12. 4 is just easy to draw. It's easy to split things in half and halves again. And they give us a good enough visual of what's happening to be enough. So our idea is to take these 4 sort of rectangular width sections. They're all equal in width. That's how we've drawn them. At least we're trying to draw them. And we're going to try and create a rectangle with them. The tricky thing is deciding what the height of that rectangle is. So there's 3 ways that we can choose the height of our rectangle. We could choose to let the height of there's not just 3. There's 3 we're going to talk about. We could choose to let the height of our rectangle be the left-hand endpoint. Okay? So we just draw the triangle or the rectangle over like this. Obviously, that overestimated my area, right? If I took that area, that's a little bit too much. Another option is we could use the right-hand side to make the area, to make the height of our rectangle. Then I've underestimated it. Yeah? It's not quite enough. Or we can do like, Goldilocks. We go the in-between. It's just right. And it's not quite just right, but it may be better in general to use the midpoint halfway. So if I use the midpoint halfway, I might have a location sort of like right here. And I'm going to use the height right there instead. So it would be something like this. And I would draw this height in. So it's a little bit of an overestimate, a little bit of an underestimate. It might be balancing the two a little bit better, but that's a third option. And these aren't the only 3 ways to do it. They're just the only ways we're going to focus on. Another way to do it that's commonly done is to use trapezoids. So if you use trapezoids, it means you connect these 2 like that, and you find the area instead. That's another way to do it. We're not going to focus on that, but it is an option. So the first one we're going to look at is the left-hand endpoints. What happens? So with this method, we're going to use the left-hand endpoints, and we're going to draw them all in. So I'm going to draw in the left-hand point, and I'm going to make that my height. So it's going to go over, and then it's going to go down. And I'm going to do my left-hand endpoint for the next rectangle, and it's going to go over, and it's going to go down. And then I'm going to use my left-hand endpoint for the third one. And all of a sudden, because of the shape of the curve, you'll notice that now it's an underestimate. So what seemed to be too much is now too little. And even more so for my next one. So I've overestimated on a couple. I've underestimated on a couple. For this one, it's probably a pretty good estimate if I just used the left-hand endpoints. Seems like it might be visually, right? Yeah. So the formula or the equation that's happening when you're doing this is you're finding area, and you know how to find the area of a rectangle. How do you find the area of a rectangle? Okay, stop whispering. Somebody say it out loud. Base times height. Thank you so much, Levi. It is base times height or length times width, right? Some of you were saying length times width. I could hear it. Yeah, it's just the 2 dimensions that are there. So here's what we're going to do. We're going to figure out, I'm going to do L of x. I don't usually like using L, so make sure yours really don't look like ones. L of x for left hand, okay? And we're going to find the length and the width. Now, if we've divided them well, all these widths are the same. Agreed? that was my goal when I drew them that way, was I was trying to anyway. And we're going to call that width delta x. Delta means change in. It's just the change in x. So each one of these widths are the change in x. So I have the change in x times the height of the first rectangle. Well, I need a little notation. Let's call this point, which I originally called A, we're going to now call it x0. And then x1, x2, x3, and this point B down here is going to be x4, which we'll use on the other screens too. So the width is delta x. The height is this first y value at x0. We have notation for that. It's called f of x0. Okay? So the height is the y value, so we're multiplying the width delta x times the f of x0. That's area number 1. I'm going to need 4 of them. Area number 2 is delta x. What's the height of my second rectangle? Right, it's f of x1. Rectangle 3, delta x. What's the height of my third rectangle? And then, okay, I'm running into things coming a little too high. Let's move that down. And then I have the delta x, and this one's f of x3. Notice I don't need the x4 on this calculation. I will on the next slide, but I don't need it here. But look at this. Every term has a multiplication factor in common, right? So what we could do instead is we could write this as delta x in front, and then we have f of x0 plus f of x1 plus f of x2 plus f of x3. Okay, I should probably reorganize my slides a little bit since I'm going down here now, but that delta x is in front, that's fine. Do you see these f of x1, 2, 3? Starts to look like stuff like this, doesn't it? These a sub things, right? This is the one I wanted. I'm adding together a bunch of things, like the right-hand side of this with subscripts. So a more concise way of writing this that would allow us to use those formulas if needed is that this is the summation from I equal, and ours started at 0. It was I equals 0 to 3 of f of xi. That's what it is. Now, if it's small numbers, like I only have 4 values here, I'm probably not going to use those formulas. But if there were a bunch of values, we might be wanting to do so, right? If you had 16 rectangles, or 32 rectangles, or 100 rectangles, you're not going to do that by hand, and then you could use the formulas themselves to figure those things out. Okay? This is left-hand endpoints. The right-hand endpoints works much the same. So this is x0, x1, x2, x3, and x4. But instead of using the left-hand endpoint, I use the right-hand endpoint. So I get this rectangle. And then I get this rectangle. So those are both underestimates, but then when I shift to the other side, now I'm going to start to get those overestimates that I was getting before. And it looks like that. Again, this wouldn't be too bad because I got a couple unders, a couple overs. It probably would balance out fairly well. Notationally, just like before, I can rewrite this. So this is the delta. I won't write all the pieces out. I'm going to call this r of x because I'm using the right-hand endpoints. It is delta x. And then for this one in particular, I would have f of x1, f of x2, f of 3, and this time I do need f of x4 because the heights here are determined by the x values that are on the right-hand side, which is x1 to x4. And consolidated notation that looks like what we've done actually looks closer to what we've done. It's the summation from I equal 1 to 4 of f of xi. So left-hand endpoints and right-hand endpoints are the easiest of the two options. Midpoints gives us better estimations in general, but it's typically a little bit more work. And I don't have a concise, compact way of writing it nicely. It's a messy, you can write it this way with the summations, but it's really ugly. So what we're going to be doing is we're going to be dividing these intervals in halves. So I divide this into half, half, and half, and I use those heights. So I'm drawing my height across at the height of the midpoint instead. Okay, that's not perfect on my pictures, but it's not too bad. And we would be overestimating, underestimating for this equation, mostly on every interval. Every piece has an over and underestimate. Okay, so we're going to do an example with 4 rectangles. I don't think I ask you for any more than 8, I think, in your homework. So it's not too bad. And you're going to want your calculator out. So grab your calculator if you don't have it out. It wants us to do left-hand endpoints, right-hand endpoints, and midpoints. And our equation is 2x squared plus 5. Our interval is from 0 to 2. And while you don't necessarily have to draw out every one of them, I do think it's helpful to at least draw out the interval along the x-axis to divide it up. So I'm going to draw an estimation of this graph. An estimation, this is the graph of a parabola opening upward at a height of 5 on the y-axis. So it's going to look something like this. I'll make mine a little wider. And it's going to go from 0 to 2. And I need to have 4 rectangles. So I have to subdivide in half, so that's 0 to 1. And then in halves again, which would be 0.5 and 1.5. Fractions or decimals are fine, doesn't matter. So I'm not going to draw 3 separate images, but I'm going to reference this image to figure out what it is I need. So my left-hand endpoints, well, in fact, all of the intervals hinge on the width. What's the width of each of my rectangles going to be? It's 0.5. Okay, so that's dependent upon the problem that you do. If this interval had been from 0 to 12, and I had 4 rectangles, it wouldn't be 0.5. It'd be 3. Okay, so you have to figure that out each time. In this picture, right here, the delta x is 0.5. So at the beginning of each of these, I have 0.5. And then I need the heights of the left-hand endpoints. So what is the first left-hand endpoint's x value? 0. So I'm going to use f of 0. The second one is 0.5. The third one is 1. And the last one is 1.5. Now, we could find those 4 values in a table. That'd be fine. We could find them by hand, just calculating. And we could probably do this one pretty easily in our head. Maybe not with the 0.5s, but for the 1 and the 0 and the 1, we certainly could. But I'd like to show you a real quick calculator trick. And then it's actually able to be used for all of them very nicely, especially when we get to the midpoint one, which is a little messier. So I'd like for you to enter the 2x squared plus 5 in y1. And I don't have a document camera, I'm sorry about that. Okay, back in your regular screen, okay, ignore the 0.5 part for now. Just ignore that beginning 0.5. I want you to type vars, find the vars button. So you're looking for vars. You're going to arrow over to yvars. You're going to select option number 1 that says function. and then underneath that, you're going to select option number 1 that says Y1. Did everybody find all those buttons? Are you good? So if I press enter on my screen right now, it just says Y1. If I press enter on top of the Y1 at the last step there, it should just say Y1 on your calculator, does it? Okay, next to it, I want you to put parentheses, if your calculator didn't already do that, and put 0. This is the same as the f of 0 notation. Your f function is the y1 in your calculator. If I press enter right now, it will tell me the y value when the x value is 0. I know it's 5 because this is not a hard one to calculate, so if you want to check it, go ahead and hit enter to double check that. But what I really want to do is I want to add all of them together. So I can do plus, and I can do vars, y vars, function y1 of 0.5, plus vars, y vars, function y1 of 1, plus vars, y vars, function y1 of 1.5. And if we do that, we get 27. And then you can multiply it by 0.5 or divide by 2 if you prefer, and you will get a 13.5. Okay, so for your right-hand endpoint, it'll be very similar, right? It's the same width, so the 0.5. And then instead of starting at f0, you're going to start at f of 0.5 because you need the 4 right-hand endpoints. So it's 0.5, 1, 1.5, and 2. And then if you've already done this in your calculator, it's really kind of nice. So on the TI versions that you're working with, if you hit second enter, it will bring up the previous line that you've typed in. But if you do it again, second enter, it will bring up 2 lines in the past. So you could actually take out the y1 of 0 and put in a y1 of 2. If not, you can certainly enter that all by hand again. That's not a problem, and it will give you a summation. Okay, so my calculator is telling me I have that summation to be 35. And then if I multiply it by 0.5 or divide it by 2 equivalently, I'll get 17.5. Okay, so I'm going to make this just a little bit smaller, and we're going to do the third one, the midpoint one. So I didn't give you notation, but for midpoint, we're just going to call it the m of x because it's the midpoint. And we're going to do the same thing. We have a 0.5. But we need those in-between values, like we pointed out. So we need values that are sort of halfway in between each of these. I'll put them in red and we'll mark them. So halfway between 0 and 0.5 is 0.25. Halfway between 0.5 and 1 is 0.75. 0.75. Halfway between 1 and 1.5 would be the 1.25. And then halfway between 1.5 and 2 would be 1.75. So over here, we're going to have f of 0.25 and f of 0.75 and f of 1.25 and f of 1.75. Again, you can enter that all into your calculator. And if you do, you're going to have that same 0.5 at the front, and it will be times 30.5. And multiplying those together gives you 15.25. So these are the 3 answers that you get for the 3 questions it asked you.